Hi everyone, I am excited to share my new findings. I ran the simulation as discussed previously. I am simulating a single beam, a single proton beam in a simple water phantom. And I have done some more experiments with with only water phantom so far, but soon I'll jump into heterogeneous material. Anyway, let's start. So what I first did was, this is the case of Fred. I have already shown you the codes that I used for Fred and MC square to obtain these, to create this simulation. So for this case, I made I made the beam monoenergetic. The energy of the proton was that proton beam, which contains 1 million protons, that has energy of 150 MeV. And when I say the energy full width half maxima is 0, that means the beam is monoenergetic. And when I say it's 5 MeV, it means the energy of the protons may vary from 145 MeV to 155 MeV. It's not monoenergetic. So what I observed was, the range of the proton beam with the monoenergetic proton beam is greater than non-monoenergetic, the real beam case. And it can be seen here that the peak occurs at 155 millimeters inside the water phantom, and here 153 millimeter inside the water phantom. But apparently it's not visible here. It seems this might be greater, but it's easy to fool ourselves. Um, Now, is that the same case for MC square? Indeed, MC square shows the same output for the monoenergetic proton beam and the uh, non-monoenergetic proton beam. And we can see from this dose maps that the range here for monoenergetic protons is greater, and that is also quite clear from the integrated depth dose plot. Now, why that could be? The answer is, when the protons have single energy, they are more narrower in the sense that all the protons will deposit their energy at the same depth. And you can see it's more sharp here than here. Also in the case of Fred, you can see that it's more blurry here than here, because all the protons of same energy are depositing energy at the same depth. And now the question is, why at higher depth? Because the protons in with the protons which are non-monoenergetic, some of the protons, like the protons with energy of 145 MeV, they deposit the energy closer to the surface at the narrower. So the Bragg peak gets shifted towards the narrow, and it's a bit broader than the monoenergetic peak. And because of that shifting, the you also see the rise of the peak is a bit not as steeper as this one. Here it rises quickly, but here it rises not that quickly. It's because the energy, the protons with less energy, they are pulling the Bragg peak towards front. You may ask also, there are protons which are higher, which are of 155 MeV. They might also be pulling the peak towards depth. That's a good observation, I would say, but the peak is getting broader because of both of the cases, and the energy is getting the peak is getting pulled forward towards the surface because of this non-monoenergetic. I hope I'm clear. Also, if you see the the distal fall off, this fall is not as sharp as this one. It's it falls quite rapidly, and this one not so rapid. Now I tried to make the the beam. I'll keep it as non-monoenergetic, which is the real world case. But now I will make the beam as point beam, spot size equal to 0. That means the beam will be, there will be no spread in the beam when it enters the phantom. Of course, once it enters the phantom, there will be uh, the beam will spread because it will interact with the material. But when I before when I produce the beam, I want it to be a point beam. For Fred, I can simply put the emittance equal to 0. That will make the beam spot size equal to 0. I don't have to play with other twist parameters which I have shown in my previous videos. Now this is what I get for making the beam spot equal to 0, making it spot beam. So my beam is now the spot size is equal to 0. This is the how do you say it? This is, you look from above and the beam is going from you to the screen, and you're looking from above the screen. I hope I'm making sense. And this is that profile, and this is the beam coming at you for beam spot equal to 0. And for that I also got the integrated depth dose. I hope you're paying attention to the almost maximum peak value of, it's around 10 to the power minus 12 of Fred. And for MC, oh, I have not multiplied it with, there is this coding error, I'm telling you. You won't believe me, but wait. For example, see here the unit matches. So the error, I know what's happening here. It's I I use, for example, MC square dose equal to MC square dose times 10 to the power minus 12 to convert it from electron volt per gram to gray. And because the variable names are same, if I run it twice, it 10 to the power minus 12 times 10 to the power minus 16, it's becoming 10 to the power minus 27. But I'm aware why it's wrong. Believe me guys, it's 10 to the power minus 12. And yeah, okay, also I have rotated the beam. It's for this case the beam is, it doesn't matter, I'm just showing you how the beam looks when the beam spot size is equal to 0. You might say for this the beam is coming from this direction, for this the beam is coming from this direction. I can just rotate it, not a big deal. But this is what it looks like in Fred and in MC square. Okay, also now I am showing you the integrated depth dose for various energies, for 3 energies. And what I find is all of them uh, overlap very accurately. That means they validate each other quite accurately. Now, you might see this dose is this peak dose for it's this dose are the value of the Bragg peak here. Now you might notice that the peak dose decrease with increasing energy for Fred and for MC square, and almost all of these two values are almost similar. You can see 3.80, 3.74, it's 10 to the power minus 7, it's very close. You might also wonder why I am putting the unit as gray times millimeter square. It's, I mean, the SI unit should be gray times centimeter square, but here my I'm keeping the pixel in millimeters, and just to make things a bit easier to convenient for me, I have kept it like this. And of course the unit is gray times millimeter square because I further I will try to study how changing the voxel spacing affects my Bragg peak and lateral peaks, which which I'll discuss with you maybe in the future. Now, the question is, why do peak dose decrease with increasing energy? You see, when the energy increases, our Bragg peak shifts deeper. It goes deeper. When it goes deeper, that means the proton has to lose more energy while traveling to the peak. So it loses most of, not most of it, but quite a big amount of energy when it travels farther deeper in the tissue or water phantom. Because here the proton does not goes very deep, the peak, the energy comes, almost all of the energy is at here at the peak. Now it travels, it loses energy, and the remaining energy comes here. That means the energy here will be lesser than the energy here because it has traveled. Same goes for this one. You will see this energy decreasing, the dose decreasing. Now the question is, why is Fred's Bragg peak shallower than MC square? Yeah, you see, the Fred's Bragg peak appears at 102 millimeter, 103 millimeter, 154, and you might think that there might be not proper overlapping of the geometry, but which I will tell you which is not the case. I'll show you further. um, so that happens because of the physics behind this algorithm, or behind this Monte Carlo codes. So in Fred, they use pre-computed lookup tables. They use data from P star. They compute how much energy will be lost for this interaction, and they put it in a table. And when Fred is running the transport, it just interpolates from those table, takes the values from those table, and which is quite accurate, but not as accurate as MC square, which is quite faithful to the physics. It numerically integrates at every step during the transport using this Kaura cow. I hope I know I'm mispronouncing the name. I'm sorry, but yeah, Kaura cow method, using the integrated, and that's how they find the stopping power, or how much energy gets lost. And that's why Fred underestimates by it's not a big difference, but that's why the peak is not exactly at the same position. MC square is quite accurate because it numerically integrates at each step, which makes it a little bit slower but accurate. However, Fred is also accurate but faster. So to make it faster, we have to uh, pay some prices. So that's the price, but it's, I would say it's accurate as well. They have done the validation and commissioning. It's quite accurate. Fred is quite accurate. I'm telling you the reason for the Bragg peak to becoming 1 millimeter before the MC square. Now I told you that that is not the case for the geometry, because I plotted the lateral profile, and if it would have been the case of the mismatch of geometry, my lateral peak would have also come, would not have overlapped, right? So that's of course not the case of geometry mismatch. Anyway, now you will see that, okay, here my dose was in the range of 10 to the power minus 7. Here 10 to the power minus 6. How come the dose in my lateral profile is more, 10 times more than the Bragg peaks? Of course, when I say the dose, maximum dose, I'm always talking about this peak dose. And yeah, so the first thing that you notice is this: why is lateral peak dose is more than Bragg peak dose? Which I'll come back to you. What else do you see? You see that the dose is almost the same for all the energy, but also, I mean, it's almost same, but you can also see that the dose increases this time with increase in energy, the lateral peak dose. Yeah, this time it's increases for the peak, and the previously it decreased. And you know the reason for the decrease, with decrease peak do how to say it? Yeah, the peak dose is lesser for greater energies for bragg peak, but here it's the opposite case. And yeah, also I just mentioned this part. Why? Wait, that's just an, okay, that's what, okay, fine, fine. That was some animation problem. So for integrated dose peak, my, let's say the proton beam is coming from z direction, and it's depositing its energy in the water phantom. Now for integrated depth dose for bragg peak, I computed the dose deposited in each slice, but in this plane. So in this plane, let's say it deposited 5 gray per dot millimeter square times millimeter square. In this slice, it deposited 7 gray millimeter square. In this slice, it deposited 10, and then 20, because you get bragg peak here and it goes to 2 or something. So that's how I got the bragg peak. I'm computing the total sum times the voxel size. There are small voxel, square voxel here, times the voxel, and I get the dose in each plane, and then I plot it uh, for plane that is z equal to 0 here, 1 here, 2 here, you know. I hope you get the idea. That's how I plotted. For this, I sliced the phantom in longitudinal direction parallel to the beam. So when the proton beam is going through this direction, all of the proton, because the proton will travel mostly in very straight path, of course it will scatter, but most of it will stay on the on a straight line. So most of the energy will be deposited in this slice. Hence all, I mean almost all of the energy. Hence you get the 10 to the power minus 6 um, for this, because I'm plotting. So for this it will be 0 0.5, 0 0.5, 0 0.5, 0 0.5, and you know, maybe 20, 30 gray millimeter square, then 0 0.5, 0 0.5. You get the idea. And that's how I plotted. I took the sum here, I plotted z equal to 0. This value belongs to here, this value belongs here, and this peak comes in this slice. And I hope I'm making sense. As a result, the entire dose is deposited in this slice. So we get 10 to the power minus 6 gray times millimeter square. And what was the other question? Why peak to, yeah, I answered this one. Why is lateral peak larger than bragg peak? And why peak dose increases with energy? So you see, for 180 MeV, we have greater energy deposited compared to this one. It's not quite large, the difference, but still. And you can see now, because 180 MeV protons is has yeah 180 MeV protons have more energy than 120 MeV protons, and we are taking this slice, the complete energy deposited. As a result, we will see that 180 MeV 180 MeV protons lateral peak will be larger than 120 MeV protons lateral peak. I hope I'm clear. Now, yeah, you can see this is the lateral profile for 150 MeV point beam. That is, the spot size is equal to 0. And here the spot size is not equal to 0. It's the default value set by uh, the the MC square and Fred. At the starting of this PowerPoint, I showed you how I made the spot beam equal to 0 for Fred. For MC square, I changed the value in their BDL file, the beam data library file. I made the energy spread equal to 0, or well, they were not accepting exactly 0 value, so I took the value of 10 to the power minus 3 and made it um, uh, almost the spot size equal to 0. Why 10 to the power minus 3? Why not 10 to the power minus 6? Well, to make it computationally convenient, and also you can always ask why not 10 to the power minus 9? Why not 10 to the power minus 12? So I took 10 to the power minus 3 to make the beam spot size equal to 0 for this case, and I studied that. So what do you see is that first thing that you notice is, yeah, I gave you the answer. First thing that you notice is that not Fred, Fred's lateral profile, or yeah, this part is broader than MC square. This is because Fred uses double Gaussian model for multi-Coulomb scattering, and MC square uses single Gaussian model for multi-scattering. Another thing that you notice, when you reduce the spot size equal to 0, suddenly there is, you see, for Fred it's 5.78 and here it's 2.04. So there, even for MC square, they both rises because now the dose area has to be constant because I'm giving them the same amount of same energy of protons, so 150 MeV for both of the cases. So when I reduce the beam size, the peak, this area under the curve should remain constant because what is that, conservation of law of conservation of energy. Hence we get this higher peak for both of them, and this is slightly higher because the modeling case, the single Gaussian modeling case. Yeah, so far this is what I have simulated and got the result, and I will do some study on voxel size, how changing voxel size influences. Well, I have done it. I have to analyze the data like the way I have done it here, and then I'll move on to heterogeneous media, and perhaps I'll do, yeah, it's quite complex, but I mean, yeah, I will next will be studying linear energy transfer model, how these both perform in that case, and how the peaks and how the lateral beam spot, they, of course, when I introduce heterogeneous media, they will, the results will be quite, I mean, it will be not as similar as like this small difference. The difference will magnify and multiply, and then I'll analyze, because of the physics behind it, what's causing it. That would be, I think, the core of my master thesis. And if I get some clinical data and if I get to validate it with my simulation, that would be really good for my thesis. I know I'm being ambitious, but that will make, I mean, that will be a good study. Anyway, thank you for watching.